Ever wondered just how much a large language model truly knows? Or maybe, and this is kind of critical, what it doesn't know? Even when that absence seems, well, glaringly obvious. Today, we're embarking on a deep dive into two really groundbreaking research papers. They're peeling back the layers on how LLMs process, store, and sometimes, yeah, even fail to perceive information. Our mission today, let's unpack these fascinating concepts. We want to show you where the cutting edge research is evolving and honestly get a little philosophical about what it even means for an AI to understand anything. We'll kick off exploring one paper that really dissects how much LLMs memorize versus how much they truly generalize, essentially defining their information capacity. Then we'll pivot to a new benchmark that reveals a genuinely surprising blind spot in these powerful models, their profound struggle really to detect missing information, which is such a stark contrast to their uncanny ability to find something that is there. Okay, let's kick things off with that first idea then. When we casually say an LLM knows something you know, like it knows the capital of France or knows how to write a poem, what does that actually mean? Like technically, is it just rote memorization or is there something, deeper going on?
Well, a critical insight emerging from this research is how meticulously scientists are now separating this knowledge into two really distinct forms. So on one hand, you have unintended memorization. That's essentially the model retaining specific, often verbatim, information from its training data set. Think of it like a student who's, crammed for a test. They can recite specific answers perfectly, maybe even obscure facts, but they don't necessarily understand the underlying subject.
Right, just repeating facts.
Exactly. Then on the other hand, there's generalization. Now, this is the deeper knowledge. It's about the underlying patterns or the data generation process itself. That's more like the student who truly understands the concepts. They can solve new, never-before-seen problems, apply their knowledge creatively. And, this distinction is absolutely crucial because it helps us move beyond just saying the model knows X to understanding how it knows it. Is it just recall or something more?
That's a really great analogy, the student one. So, okay, if we're focusing on this unintended memorization, how much of it can these, well, colossal models actually hold? What's their storage limit or their capacity? Is there a quantifiable measure for it? Because these models are just enormous.
Yes, and the research offers a, frankly, remarkable quantitative estimate. It suggests that models in the GPT family, and these are some of the largest and most widely used, they have an approximate capacity of about 3.6 bits per parameter.
3.6 bits per parameter.
Yeah, and to put that in perspective, right, for a typical large model with billions of parameters, that's like memorizing the precise wording of thousands of unique web pages, or even entire books. It's not just general fact.
Wow.
And it scales linearly with the parameter count. So quite literally, a bigger model has more memory slots.
Hmm.
What's also interesting is that even if you double the precision of the data storage, say from dfloat 16 to float 32, it only gives you a marginal increase in this capacity. It moves maybe from 3.51 to 3.83 bits per parameter.
So not a huge jump.
Not really, no. It indicates a pretty robust and consistent finding. Models reliably memorize around 3.5 to 3.6 bits per parameter under these typical training settings. And what's also key is that if a data set is small enough and the model has enough capacity, it can be completely, verbatim memorized.
Yeah.
Every single detail.
That number, 3.6 bits per parameter, that really puts it into perspective. But here's where it gets, I think, genuinely fascinating. This research talks about a phenomenon called grokking. Now, I've heard the term, floating around in AI circles, but what's its real significance in this context? Because it sounds like a pretty profound shift is happening there.
Right, grokking. So zooming out a bit, the broader implication of these studies is how grokking fits into the whole learning journey of an LLM. The research reveals that models will keep memorizing specific data points until their internal capacity for just raw memorization is essentially full, like
Right.
that bucket we talked about. It gets filled up. But then a surprising transition occurs. Grokking begins. And at this point, unintended memorization actually starts to decrease as the models begin to generalize more effectively.
So they stop memorizing and start understanding or pattern finding.
Kind of, yeah. It's almost as if they realize, okay, look, I've seen enough specific examples. Now I need to figure out the underlying rules. They shift strategy. And this transition, it also aligns with something called the double descent phenomenon. It's this peculiar observation in machine learning where, counterintuitively, model performance actually improves again after an initial dip.
Right, I heard of that.
Yeah, and it happens especially when the data size exceeds the model's capacity in bits. So it illustrates this evolving understanding of training dynamics, where models transition from just rote learning to true pattern recognition They become more efficient with their stored knowledge. It's not just about adding more information, you see. It's about optimizing and abstracting what they've learned.
That transition from just pure memorization to generalization, this grokking thing, it's truly wild. Makes you wonder what specific information they prioritize, or what really sticks in that memory. Were there any surprising, nuggets about what exactly gets memorized beyond just typical data points?
Oh, absolutely. This was actually one of the most striking findings. So, while models memorize up to their capacity when trained on real text, a manual analysis uncovered a really distinct pattern in what was most memorized, the data points that stuck the most.
Mm-hmm.
They often contained extremely rare tokens, typically from non-English languages.
On English.
Really?
Right. Yeah.
For instance, the sample with the highest TF-IDF score, which is, a measure of how uniquely rare a word or phrase is, it was a sequence of Japanese words.
Yeah.
And that specific Japanese sequence, it had the third highest measured memorization among all the data they analyzed.
Wow.
And get this, out of the top 20 most memorized sequences, all but 3 contained texts from other languages like Japanese, Chinese, Hebrew, Greek.
So it's the unusual stuff that sticks out.
Exactly. It really challenges a simple notion of memorization. It shows it's not just common facts or highly repeated phrases, but also these unique, uncommon, almost alien language elements that stand out and get retained with super high fidelity.
That's fascinating that rare, non-English text gets prioritized for memorization. Now, this finding immediately makes me think about privacy concerns, particularly things like membership inference attacks, where someone tries to figure out if a specific piece of data was in the training set. If they're memorizing such precise, rare elements, does that make it easier or harder to infer membership?
Right. That's a key consideration here, the practical implications for privacy. The research actually leverages these findings to predict the performance of those membership inference attacks. And what they found is, well, it's a bit counterintuitive. While bigger models can indeed memorize more individual samples, making the overall data set much, much larger actually makes membership inference harder on average.
Ah, okay. So scale helps protect things in a way. Sort of, yeah. Their scaling laws extrapolate that most modern language models are trained on just so much data that it becomes very difficult to reliably infer membership for the average data point. The performance of these attacks, it decays toward just random guessing, like an F1 score of zero point 0.5 when you're dealing with these extremely large data sets. So yes, while models can memorize rote elements, the sheer scale of modern training data often acts as a kind of natural, albeit maybe accidental, defense against widespread membership inference attacks on the average user's data.
Okay, that makes sense. Now let's totally shift gears here for a second. If models are so adept at storing and even generalizing information that is there,
Yeah.
what happens? Tweaking, especially given how, incredibly well LLMs typically perform on tests like the needle in a haystack benchmark. Yeah, AbsenceBench. The truly groundbreaking aspect of it is how it directly contrasts with that needle in a haystack test, the NIAH. NIAH tasked models with finding a specific, often surprising piece of information that's been inserted into a very long text. Find one sentence in a million words. And LLMs, famously, they excel at this. They're really good at finding the needle.
They really are.
AbsenceBench, though, it flips that challenge completely on its head. It asks converse. Can the model identify information that has been intentionally omitted from a document? And the benchmark, it intelligently includes 3 pretty diverse domains: poetry, numerical sequences, and even like GitHub pull requests.
Yeah.
All using medium-length contexts, averaging about 5,000 tokens. It's a fundamental shift, right, from presence detection to absence recognition.
My intuition honestly tells me it should be similarly easy for these advanced models to spot what's missing, especially given how well they do on the needle test. But how do they actually perform when you ask them to find an omission? Is my intuition wrong here?
Well, your intuition is common, but yeah, the results are a massive and frankly, quite counterintuitive surprise.
Uh-oh.
Despite their near-perfect prowess in needle-in-a-haystack tasks, these cutting-edge LLMs show a dramatic, get this, 56.9% average F1 score drop when faced with AbsenceBench tasks.
Over 50% drop. That's huge.
It's enormous. For instance, some models that achieve nearly 99.5% F1 score on NIAH poetry tasks, they just plummeted significantly on AbsenceBench. And this isn't just a number, right? It fundamentally challenges our intuitive understanding of LLM intelligence. It suggests they have this major blind spot where humans, we excel. Locating omissions is fundamentally profoundly harder for these models than detecting insertions.
That's astonishing. It really is counterintuitive. So what factors make it so difficult for them to spot what's not there? Is it the length of the text, the specific type of information, or is it something else entirely? What's tripping them up?
Okay, so when we dig deeper, several factors do indeed seem to influence this performance gap. For instance, longer context length, particularly in the poetry domain, clearly makes the task harder. There's a strong statistical link there, with an R-avels value of 0.55. So it's essentially, the longer the poem, the more challenging it became for the AI to spot the missing lines.
Okay, that makes some sense. Longer text, easier to miss something.
Right. But here's another counterintuitive twist. A lower rate of omission actually leads to worse model performance.
Wait, fewer omissions makes it harder? That seems backwards.
It does, doesn't it? Imagine trying to spot a single missing step in a long staircase versus noticing a whole flight of stairs is gone. The hypothesis here is that a higher omission rate increases the likelihood of consecutive omissions. Big gaps. These might create larger, more obvious breaks that models can perhaps generate over until they hit a non-omitted element. On the other hand, fewer, smaller, more isolated missing spans. They seem to interrupt the text continuity in ways that trip up the models more effectively.
Huh. Little gaps are harder than big ones.
It seems that way. Also, prompt positioning matters. Models perform better when the instructions were presented before the original and modified documents, which suggests they benefit from knowing the task up front, setting the context.
So even with all their computational power, these models really struggle with what seems like a basic human ability, just noticing a gap. You mentioned thinking tokens earlier. Do these computational steps help them figure out what's missing, or are they just generating a lot of extra, maybe irrelevant text as a kind of workaround?
Yeah, the thinking tokens, so inference time compute, where models generate these tokens for intermediate reasoning steps.
Yeah.
It does offer a modest performance improvement, about 7.9%.
Okay, so a little bit.
A little bit, yeah. And this is but it comes at a very high computational cost. Models often generate an average of 8,000 extra thinking tokens, which is nearly 3 times the average document length of 2.7K tokens.
8,000 extra tokens. Wow, that's inefficient.
Hugely inefficient. Gemini 2.5 Flash, for example, showed the highest thinking token ratio, 5.7, and it also had a significant advantage in benchmark performance. This suggests that some models might be attempting these really computationally expensive strategies, like internally reconstructing the original document to then compare it and spot the gaps.
So it's like a brute force check.
Pretty much. It's an inefficient workaround rather than a fundamental understanding. It's like they're trying to reread the whole book just to find if the page is missing instead of just instantly noticing the gap.
Right, right. So if they're resorting to such expensive reconstruction, what's the core issue here? Is there a more elegant fix for this blind spot, or are we looking at a fundamental architectural limitation of how these models actually see information? Is it the transformers themselves?
Well, this prompts an important question about the very nature of those transformer attention mechanisms. The researchers hypothesized that these mechanisms inherently struggle with gaps. Information that's present can be directly attended to, right? It can be weighed, located. But how do you attend to absence? What do you focus on when something isn't there?
Good question.
Exactly. So to test this theory, they tried explicitly marking the omissions with placeholders, things like missing line or just a string of underscores like
Giving something physical to see.
precisely. And this intervention dramatically boosted performance. They saw an average improvement of 41.9% when using missing line.
40%, just by adding a placeholder.
Yeah, a huge jump. This powerfully suggests that the lack of a tangible span of text to attend to is a key problem.
Yeah.
It really indicates that these models struggle to anchor on conceptual information gaps unless they are explicitly given a physical marker to latch onto. It's a fascinating insight into their limitations, isn't it? Right. Showing that the physical representation of absence makes all the difference for them.
So, okay, here we are. We've got models that are incredible at storing and finding information that is there, even if it's deeply buried or incredibly rare, but they trip up profoundly on what's not there. So what does this all mean for how we understand intelligence or comprehension in LLMs? It really seems like a pretty fundamental difference from how humans think.
Absolutely. And what's truly thought-provoking here is the philosophical implication of this evolving research. Standard benchmarks have overwhelmingly focused on evaluating a model's ability to identify and reason about presence. Can it retrieve, summarize, generate based on what is explicitly given?
Right, that's mostly what we test them on.
Exactly. AbsenceBench reveals that absence recognition is a distinct foundational component of comprehension that current models seem to, well, lack. And this points to a deeper limitation. LLMs might be brilliant pattern matchers of data that exists, but they don't seem to inherently grasp the significance of what is not present. It really suggests that their understanding, quote unquote, might be fundamentally different from human comprehension, which implicitly accounts for missing information constantly.
And thinking practically, if an LLM can't tell if something important is missing, how can we truly trust it for critical tasks, especially those where completeness or accuracy is absolutely paramount? It really raises some serious questions about their reliability in real-world applications.
Oh, absolutely. Zooming out to the bigger picture, this has huge practical implications. Think about LLM as a judge applications. Things like grading essays, legal reasoning, maybe even detecting misinformation.
Yeah, crucial areas.
Right. If a model doesn't recognize that crucial evidence or a key rubric element or just a critical fact is missing, its judgment becomes unreliable. It could lead to significant errors. The current massive gap in performance between NIH and AbsenceBench really highlights how misleading current evaluations might be if they continue to just ignore absence. The research even proposes that this absence failure might be a useful conceptual lens to understand other weird phenomena like hallucinations or misjudgments, suggesting maybe a common underlying limitation in their comprehension.
So it could be a piece of a larger puzzle about LLM failures.
Could be. And this also prompts an important question for the future of AI development, doesn't it? Does this mean we need completely new architecture, something beyond the transformer, to truly address this blind spot? Or are there clever, more efficient ways to maybe teach them to see absence within the current framework? The research itself points to the need for a much more mechanistic understanding of why this failure occurs and how the attention mechanism specifically is connected to it. It's definitely a critical area for future architectural and inference time research, really pushing the boundaries of what these models can genuinely comprehend.
Wow, what an incredible deep dive we've had today. We started by exploring the inner world of LLMs, really understanding how much information they can store and generalize right down to the precise bits per parameter, and learning about their surprising memorization of rare, often non-English elements. But then we uncovered this fascinating, almost unsettling blind spot, their profound struggle to detect things that are simply missing, even when the task is explicitly designed to highlight those omissions. It really makes you pause, doesn't it? Makes you think about what it means to be truly informed or aware. It's not just knowing what is, but crucially understanding what isn't. For you listening, whether you're, prepping for a meeting, catching up on a cutting edge field, or maybe you're just intensely curious like us, this highlights that while LLMs are undeniably powerful tools, true comprehension, well, it's a multi-layered concept that even the most advanced AI is still grappling with. It leaves us with a provocative thought for you to mull over. If AI can't reliably detect absence, what other fundamental aspects of reality, or even just common sense, might it be missing right under its digital nose?